Our solar system is a magical place. Countless worlds are scattered across billions of kilometers of space, each being dragged around the galaxy by our sun like a complicated clockwork. But how did we get our solar system? Why are these objects in their present location? In this video, we'll take a look at everything you need to know about the history of our solar system and what the future awaits. The universe was created 13.8 billion years ago by the Big Bang. Our solar system came into being much later, around 4.6 billion years ago. It began as a massive cloud of dust and gas created by leftover supernova debris. The death of other stars gave birth to ours. The cloud that orbited the center of our galaxy was mostly hydrogen, with traces of helium and heavier elements forged by previous stars. The cloud collapsed under its own gravity over the next 100,000 years, forming hot, dense protostars, one of which was our sun. Our baby sun continued to accumulate material for 50 million years, until temperatures and pressures in the core became so high that hydrogen began to fuse into helium. After that, there was light. Hydrogen fusion produced enormous amounts of energy, which counteracted the sun's gravity, stabilizing the young star and preventing it from accreting more material from the rotating disk of leftover debris around it. The sun entered its most active phase, becoming a main sequence star. It is still in this stage today and will be for the next 5 billion years. The sun separated from its stellar siblings after 500 million years and continued to orbit our galaxy's center as a lone star. While the infant sun was still gathering material to begin fusing hydrogen, tiny dust particles in the disk around it randomly collided and stuck together, growing to objects hundreds of meters across in just a few years. This process continued for thousands of years, resulting in kilometer-sized objects large enough to attract each other gravitationally. This resulted in more collisions and accretions, resulting in the formation of moon-sized protoplanets in less than 1 million years. Planets formed primarily from rocks and metals in the inner, hotter part of the solar disk because it was too hot for water and other volatiles, substances that evaporate at room temperature, to condense. For about 100 million years, hundreds of these worlds collided and combined in the inner solar system, leaving only 4 large bodies: Mercury, Venus, Earth, and Mars. Because the percentage of rocks and metals available in the universe, and thus our solar system's starting materials, is lower than that of hydrogen, helium, and volatiles like water ice, the inner planets did not grow as large as the outer planets. The solar system became more peaceful after the late heavy bombardment. Asteroid impacts still occur, but their frequency and size have decreased dramatically. There is still cause for concern because the following relatively large impacts occurred in the last 100 million years. An asteroid or comet collided with the Moon 108 million years ago, forming the 86-kilometer-wide Tycho crater visible from Earth. The dinosaurs would have been alive and well to witness this occurrence. Saturn's famous rings formed during the same geological epoch. An asteroid 5 to 15 kilometers wide collided with Earth 66 million years ago, causing global climate change. This wiped out 3/4 of all life on Earth, including the dinosaurs. The collision of Comet Shoemaker-Levy 9 with Jupiter in 1994 was a spectacular but sobering event witnessed by telescopes all over the world. In 2013, an asteroid exploded over the Russian city of Chelyabinsk, destroying buildings and sending over 100 people to nearby hospitals. Our planet is still vulnerable to dangerous asteroid impacts, emphasizing the importance of planetary defense. Stars, like all good things, must come to an end. All stars, including the sun, will eventually die, and the universe will fade to black. For the time being, the sun can keep going by constantly converting hydrogen into helium. This process, known as nuclear fusion, generates enough outward pressure to counteract the sun's relentless gravitational pull. The sun is currently consuming 600 million tons of hydrogen per second, and there will come a time when there will be no hydrogen to burn. Despite its voracious appetite for this abundant element, astronomers estimate that the sun has approximately 5 billion years of fuel remaining. When the hydrogen runs out, gravity takes over and the sun's core begins to collapse. With the solar material significantly compressed, the temperature in the core will reach a mind-boggling 100 million degrees. In comparison, there are currently 15 million degrees in there. Meanwhile, the pressure will exceed 1 trillion times that of Earth's atmosphere. Because of the extreme temperatures and pressures, helium becomes an ingredient rather than a product. and it is pressed into carbon and oxygen. Every second, the Sun will consume the equivalent of 10 Earth masses of helium. This helium burning occurs at a much faster rate than the previous steady-state hydrogen burning. The delicate balance within the Sun has now been upset in the opposite direction. The outward pressure is so great that it overpowers gravity, causing the Sun to bloat into a red giant. It will eventually grow large enough to swallow Mercury and Venus, and it may even swallow Earth. In its final death throes, the Sun will eject its outer layers into space, much like a snake shedding its skin. Astronomers refer to the beautiful, glowing, and nested shells of gas created by this as a planetary nebula. A white dwarf, a ball of carbon and oxygen the size of Earth, will be nestled at its heart. This is all that remains of the Sun's once mighty core. For decades, astronomers have speculated about the true impact of the death of a Sun-like star on its system of planets and moons, specifically whether any planets can survive the onslaught. We now have some ideas, thanks to a breakthrough discovery. While the dying Sun will most likely destroy the terrestrial planets, the outer planets may survive. This is a novel approach to searching for alien worlds because the two most common methods rely on detecting changes in the light of the host star. When a planet passes in front of a star, it dims, or we see changes in the starlight caused by the star wobbling due to the gravitational pull of an otherwise unseen planet. By eliminating the need to see the star's light, more strange and wonderful worlds, such as those swirling around dead stars, can be discovered. The team was not looking for planets orbiting dead stars at all. Instead, they were looking for worlds revolving around ordinary stars in their prime. The light from a background star was magnified by the white dwarf, but the light was warped by the presence of a planet. This planet is 40% more massive than Jupiter and orbits the white dwarf roughly twice as closely as Jupiter does the Sun. We might not have to wait long for the floodgates to open, allowing more discoveries like this to pour in. The Nancy Grace Roman Telescope, which is scheduled to launch in 2027, will be able to image giant planets orbiting white dwarfs near the center of our Milky Way galaxy. For the first time, we'll have a more complete count of these cosmic survivors, and we'll learn a lot more about our own solar system's future. We will learn whether Jupiter-like planets are the lucky few, or whether it is common for Jupiter-like planets to survive their stars dying. These long-lived gas giants are intriguing because the death of their stars could transform their moons into potentially habitable worlds. Astronomers frequently refer to a habitable zone, which is a region around the star where the temperature is just right to support the presence of liquid water. This region will be pushed much further out by an expanding dying star. Jupiter and Saturn, for example, have icy moons called Europa and Enceladus in our own solar system. Approximately 99.9% of the water in the solar system exists outside the realm of the terrestrial planets. During the red giant phase, the host star's increased luminosity may melt the icy shells of these frozen water worlds, revealing the liquid water oceans beneath. It may grant our ancestors a stay of execution. Whatever forms of life remain after 5 billion years would have a better chance of survival if they relocated to one of Jupiter's moons. However, this would only be a temporary reprieve. To stay warm, you'd have to be 100 times closer to the white dwarf than the Earth is now to the Sun. This constraint could be relaxed by an unusually hot white dwarf, but it would also emit massive amounts of radiation that life would struggle to deal with. Finally, unless you plan to leave the solar system, the death of our star is unavoidable. Everything comes to an end, so make the most of it while you can. And with that being said, it's time to end our video. Subscribe to the channel for more amazing videos like this. We'll see you with another interesting video.